Hey everybody, I want to talk to you about confidence intervals. This is kind of a big topic, so yeah, let's get going. So the first obvious question is, what is a confidence interval? And so what a confidence interval is a way to provide a range of reasonable values for a parameter. So it's a way of estimating a parameter, essentially. And so what we're going to do is, since we don't generally know the value of a parameter, we're going to estimate it from a statistic, right? We're going to take a sample, we're going to find the statistic that goes with the parameter, and then we're going to make an interval around that value. So for instance, what we're going to be doing in this section is talking about intervals for the population mean. So if I want to find if I want to estimate what the population mean is of something that I don't know what, like some population that I don't know what the mean is, what we can do is we can take a sample, find the sample mean, and then wrap an interval around that. So we're gonna find our sample mean. We know that our sample mean isn't actually equal to the population mean, but it's probably reasonably close. And we'll talk about what probably and reasonably close mean in just a couple of boards here. But we're going to use that as like our point estimate for what we think the population mean might be. And then we're going to go a certain distance on either side of that, which we'll learn how to calculate in a second, called the margin of error. Like we're going to provide a margin of error around that value that we get and say, well, we think we're pretty confident that it's in here somewhere. We don't know where, but we think we think the population mean is in here somewhere. All right. So with that in mind, let's see what we do. So yeah, that's basically the main idea. So here is sort of the basic idea. So each different sample is going to give us a different confidence interval, right? Because each sample doesn't contain the same data. Now, we're not actually going to take more than one sample. I'm just using this to illustrate, well, what if we got this sample, or what if we got that sample? Sort of as let me back up there. I want to use that to illustrate what can happen depending on, which universe we live in, right? The universe we live in where we got sample 1 or sample 2 or sample 3. So here's the idea. Let's say my population distribution actually looks like this. Now, this is a thing that when you are taking your sample, you don't actually know. We have no idea what the population distribution is. We don't know what the population mean actually is, because how would we, right? That's what we're trying to figure out. So why would we know what the distribution was to begin with? We don't. All we have is this information about what our sample was. So let's say I take my first sample and I get this as my mean, and we'll go over the procedure for how to make a confidence interval in just a second, but let's just say it's this interval right here. So this distance right there, that's the margin of error. That's how far you go from the mean to one edge of the interval. Right? We're going to start at the mean and then go margin of error distance away from that in order to make our interval, which again, I'll show you how to do in just a minute. And by the way, I'm calling the margin of error E, capital E. I think that's what your book calls it as well. I don't remember for sure, but that's what I'm calling it. Is capital E for margin of error. So for our first sample here, we get this interval that with a margin of error of E1. And for the second one, we get this interval here. It's got a margin of error of E2. Same thing for sample 3. The thing I want to point out is sample 1 and sample 3, the confidence intervals associated with sample 1 here and sample 3 actually do contain the population mean, right? Here's mu. It actually is inside the interval for sample 1 and sample 3, but not for sample 2. It is possible that we can get a weird sample that doesn't actually contain our population mean, or weird samples whose confidence interval doesn't actually contain our population mean. So let's see how to tell how confident we can be that the population mean is actually in our interval. So here's the logic that we're going to use. the basic idea is that you want to see here is if x is within a certain distance of y, then y is within that same certain distance of x, which probably sounds obvious to you, right? If I have two things that are, what is it, like 8 inches apart, this first thing is within 8 inches of the second thing, and the second thing is within 8 inches of the first thing, right? Distance works both directions. In math, we call that reflexivity. So our default is that we want is to use 95%. We're going to be 95% confident that the population mean is actually within our interval. So here's how we go about doing that. So here's the idea. So the x and y that I was talking about here, I want to think of those as mu and x bar. So here's what I mean by that. If I want to be 95% confident that our interval contains mu, which is what we're trying to do here, then here's the logic. So let's say this distribution is the actual population distribution. Now, the researcher doesn't know what this is, has no idea, and has no idea what mu is either. However, we do know that if we are within, well, for normal distributions, it would be 1.96 standard deviations of the mean, then we get 95% of our data. Now, that's different for t-distributions, right? If you watch the t-distribution video, you saw that it's not just 1.96 on either side. It depends on the degrees of freedom, right? So it depends on what n is, because that'll determine your degrees of freedom. So we're going to have to find these all individually. But the basic idea here is, let's say that, I'm doing whatever, 20 degrees of freedom, right? I take a sample size of 20, a sample of size 21. So I've got 20 degrees of freedom. I want to see how many standard errors I need to go on either side in order to capture 95% of my data. So I'm going to do inverse t, just like we did in the t-distribution video, like this. So t dot inv equals, I was right, equals t dot inv. Probability, I want to go 0.025 with 20 degrees of freedom, I said. So that means I need to go 2.086 standard errors on either side of the mean. So let's go do this. So this margin of error, this is 2.086. This is 2.086 standard errors. On either side of the mean. And what that'll do is that'll get me 95% of the data. You might say, well, wait a minute, I thought we didn't know what mu was. How can we know where that would be if we don't know where mu is? And here's what we're going to do. The idea is, if x1 is within 2.086 standard errors of, or x1 bar is within 2.086 standard errors of mu, then mu is also within 2.086 standard errors of x1. So what we do is we don't try to go 2.086 errors, standard errors from the population mean, because we don't know what that is. What we do instead is we go 2.086 standard errors from the sample mean, right? And so if E is this distance right here, I don't try and aim it, I don't try and center it on mu, I try and center it on x1 bar. And by doing that, I get an interval that looks like this. Right, where this distance right here was E. That was the 2.086 standard errors. Now, since 95% of all possible samples that I would take are going to fall within this black shaded area, then 95% of the samples that I take, or how can I say this? And that distance from mu to the edge of the shaded area is 2.086 standard errors. Well, then 95% of my mean of all my samples will have a mean in that range. So that also means that if I go that same distance from the mean, from the sample mean, 95% of all my sample means will have the interval that I make include mu, right? The idea here is that if x1 is within 2.086 standard errors of mu, then mu is also within 2.086 standard errors of x1 bar. So the confidence interval that we make is this. It's this right here. And we're 95% confident that mu is in there somewhere. Now, given the picture, obviously we know mu is actually in there, but in real life you don't actually know that, right? And so that's the idea. So 95% of all the possible sample means fall within 2.086 standard errors of mu. So that means that 95% of all the confidence intervals that I would make will contain mu because of that reflexivity of distance, right? And you can see that x2 bar here is outside of that 95% range. So if I go 2.086 standard errors on either side of x2 bar, the thing that I get, that's supposed to be pink. Will miss mu by a little bit. And that just happens sometimes, right? There's just no way to avoid that. So that's the basic idea of, so that percentage, by the way, that I've been saying, the 95%, it's called the confidence level. It's how confident we are that the mean is or that the population mean is actually within the interval range that we give. Not all of them will be. Sometimes, in fact, 5% of the time, if I'm doing a 95% confidence, 5% of the possible sample means fall outside of the 95% range. And so 5% of the time, the confidence interval that you make won't contain the parameter that you wanted because you just got a weird sample, right? And by weird, I mean one of the 5% most extreme samples. So that's confidence interval logic. If x1 or if x bar is within 2.086 standard errors of mu, then mu is within 2.086 standard errors of x bar. So we wrap that, so we make an interval that is 2.086 standard errors wide around x bar, and then we can say that we're 95% sure that mu is in there somewhere, although we don't know where. So that's what a confidence interval is a range of reasonable values for our parameter, in this case mu. Now you can actually make confidence intervals for any parameter, but you have to know the sampling distribution of that parameter. And the only sampling distribution we currently know how to calculate is sampling distribution for the sample mean or for the sample proportion, right? From the central limit there. That's where we're getting these from. Okay, so margin of error. This is probably a rehash, or this is roughly a rehash of the thing I just said. So confidence interval for the population mean is going to be our sample mean plus or minus our margin of error, like I said, with the margin of error being calculated so that we are capturing some percentage of the sampling distribution. I've been saying 95%, but it could be anything. We could do an 80% confidence interval or a 99.5% confidence interval or whatever number we want by using the inverse norm or inverse t functions to figure out how many standard errors we have to go. So if we want to be 95% confident, which is the standard amount, by the way, that's basically every confidence interval you've ever seen has probably been a 95% confidence interval. And by the way, you've actually seen a lot of confidence intervals in your life, although you may not know it. So if we want to be 95% confident, we choose the margin of error wide enough that we would capture the middle 95% of the relevant sampling distribution for the reason I just said rather awkwardly on the last board. And we can make that number whatever we want by just changing the amount of area that we're looking for with our inverse norm or inverse t function. And that percentage is called the confidence level. So here's an example. So Jason is a marine biologist. This is the data I picked from the T distribution video, I believe. So Jason's a marine biologist who has discovered a new species of fish. So he captures a sample of 11 of these fish and gets a sample mean mass of 8.56 kilograms, with a sample standard deviation of 1.12 kilograms. And we're going to make a 95% confidence interval for the population mean mass of this new species of fish. Talk about what that means. Then we're going to do the same thing for 90 and 99. Okay, so things to note here. Jason has a sample size of 11, right? So that's going to tell us we've got 10 degrees of freedom. Now, he has no idea what the population standard deviation is, so sigma. He doesn't know what sigma is for the mass of these fish because he just found them, right? This is the very first sample of these that's ever being taken. He has no clue what sigma is. So everything he's going to do, he's going to have to speculate about is going to be based on this sample of just 11 fish, right? You can go back and take a bigger sample later, but for right now, for the initial observations, it's just these 11 fish. So you get a sample mean mass of 8.56 kilograms, so that's X bar, and a sample standard deviation of 1.12 kilograms, that's S. And all right, so there's S, and we've got N is 11. So we're going to make a 95% confidence interval for the mean mass of this new species of fish. So we need to know how many standard errors we need to go on either side of the mean in order to capture 95% of the data. So let's go draw some pictures because I know this is getting a little confusing. All right, so black. All right, so let's say, so this is our sampling distribution. This is T with 10 degrees of freedom. Sorry, mu, we don't know what mu is. But we know that we want to capture 95% of our data, right? So 95%, 0.95. So the question is, how far do we have to go here? I drew that a little bit big, right? So the question is basically, how big is that? Well, our standard error, so SEM is S over the square root of N, which in our case is going to be 1.12 over the square root of 11. Right, that's our standard error of the mean. And we need to know how many standard errors we need to go on either side. So what I'm going to do is I'm going to do inverse T with 10 degrees of freedom to see how many standard errors we need to do, or we need to go on in either direction. So I'm going to go back to sheet stock. So let's go to that. So we're going to do equals T dot inverse of, so probability, 95% interval means that I want 2.5% on either side. And degrees of freedom is 10 here. So this tells me that I need to go 2.228 standard errors on either side of the mean in order to capture the area that I want. So let's go here. So this is equals 2.228 standard errors. Well, one standard error is 1.12 over the square root of 11. So I need to take 1.12 over the square root of 11 to find the size of the standard error times the number of standard errors I need to go on either side, 2.228. Right, so I'm going to go over to my calculator. So let's go to calculator. So we're going to do 1.12 divided by the square root of 11. That is the size of one standard error. I need to go 2.228 of those on either side of X bar. So I need to multiply that by 2.228. And this is my margin of error, 0.752, let's say. So I go back here, and that's telling me that I need to go 0.752 on either side, because that's 2.228 standard errors. So I did 2.228 times 1.12 over the square root of 11. Right, gives me margin of error. Margin of error. Let me do that. Margin of error. Right, that is how big this is. So what I'm going to do is find my sample mean, or take my sample mean, it was 8.56. So I'm going to get 8.56 plus 2.228 times 1.12 over the square root of 11 for the upper bound of my confidence interval. I'm going to get 8.56 minus 2.228 times 1.12 over the square root of 11 for the lower bound of my confidence interval. And we already figured out that 2.228 times 1.12 over the square root of 11 was 0.752. Right, so this is 8.56 plus 0.752. This is 8.56 minus 0.752, which we can write in a couple ways. So it's totally fine to write your confidence intervals like this: 5, 6 plus or minus 0.752. Or we can write them in the following way, which is so this is one way. The usual way is like this. So we get 8.56. I'm going to do the minus first. Minus 0.752, 2, not 0, 2. And then the same thing with plus. So 7.808 to 9.312. And this is interval notation from algebra. I don't know if you guys remember that or not, but that's interval notation. It's saying use this interval on the number line, right? Or use the interval on the number line with the left bound of 7.808 and the right bound of 9.312. So that is a confidence interval. That's a 95% confidence interval for the population mean mass of these fish. So the way I would interpret that is that Jason is 95% confident that the population, or that the mean mass of all these fish is somewhere in this range. Now, he's not 100% confident, right? His sample size is only 11. It's possibly just got a bunch of small fish or a bunch of big fish. He doesn't know, but it's 95% likely that the population mean is somewhere in that interval. So that's how I would interpret this. Then we said do the same thing for 90 and 99%. I believe that's what the other two questions were, right? Do the same thing again, but for 90 and 99% confidence levels, sure. So we're going to do exactly the same thing. The only thing that changes is this number right here. This number right here. Everything else is the same. Notice that the 8.56 was from the sample, right? That's not going to change depending on what size confidence interval you're making. Same thing for this and this, right? Those are all inherent to the sample. The only thing that changes is how many standard errors you're going to go on either side of the mean in order to capture more or less data. So if I wanted to do 90%, I would, let's go back to Sheets. So instead of doing inverse t with 0.025, I would do inverse t with 5%. Right, so for a 90% interval, I would do equals t inverse probability of 5% this time with 10 degrees of freedom. So I would go 1.812 standard errors on either side. If I want to do 99%, I'm going to do 0.5% on that side, because remember there's 1% divided into two pieces, so that leaves us 0.5%. So it's t dot inverse of, I always forget the equal sign, t dot inverse of 0.005. So that's 0.5% with 10 degrees of freedom. Tells me I need to go 3.17 standard errors on either side. So the only thing that changes from this formula here is how many standard errors, which is called the critical value, by the way. So this number is called the critical value. How many standard errors I need to go on either side. So yeah, let's go to the calculator and calculate that. I forgot what the numbers were though. So this number, so I'm going to do, what did I say? I forgot. I 100% forgot the numbers I was using. For the first one, 1.812. So I'm going to go 1.812 standard errors. So this is going to be times the size of a standard error, which is this. And so this is my new margin of error for a 90% confidence interval, 0.612. Same thing, if I wanted to make a 99% confidence interval, I would use 3.169. Get 3.169 times the size of one standard error, 1.07. That's how far I go on either side of my sample mean. So let's go write these. So 0.612. Okay, so we have 8.56 plus or minus 0.612. So this would be a 90% confidence interval. If I want a 99% confidence interval, it would be 8.56 plus or minus 1.07. 0.070, I believe. Right, and so we can figure out what these are. I'm not going to calculate them out here, but you just type that into your calculator and figure out what range you get. Now, Jason can be 90% confident that the mean is actually within this range, and he can be 99% confident that the mean is within this range. Now, I hope it makes sense that a bigger interval, which captures more area and more region of the x-axis, is more likely to actually contain the population mean. In the smaller interval that captures less area and less region of the x-axis is less likely to actually contain the population mean, right? And so ones with a higher level of confidence, a higher confidence level, are going to be wider, and intervals with a lower confidence level are going to be narrower. Now we can do the same thing for proportions. I actually want to, I want to go a little bit out of order here. I want to calculate, I want to mention this here. So the thing I was talking about is that there's a trade-off between confidence and precision. So confidence is how confident we are that the interval actually contains the parameter that we want, right? In the example we were just doing, the parameters population mean. But wide intervals are kind of bad in the sense that they don't narrow down what the value of the parameter is very well, right? If you have a really narrow interval, that's really precise. You've got a very good idea of where that parameter is. If the interval is really wide, you don't, right? So a wide interval is not great. However, the wide interval is more likely to contain the parameter you want than the narrow interval. So the high precision narrow interval is less likely to contain the mean, and the low precision wide interval is more likely to contain the mean. And that's just what the trade-off is. How much you can do about that, really? Well, that's not actually true. There's one thing you can do about that, which is to take a bigger sample. That addresses both at the same time. You can get both more confidence and more precision if you increase your sample size. However, that generally costs money. So I'm not going to get into that too much here, but basically sampling properly is expensive. And so you always want to take as big a sample as you can afford, essentially, and that'll get you the maximum confidence and precision you can achieve. But within that sample, there's going to be a trade-off, right? If you want more confidence, you're going to sacrifice precision, and if you want more precision, you're going to sacrifice confidence. And so it's just up to the researcher to decide how confident and how precise they want to be, which is why it's nice to have a default, right? This is where it's nice to say, I'm just going to do 95% confidence every time, and then whatever the precision is what it is. That's a very standard choice to make. Okay, so we can also make confidence intervals for proportions, because we also know from the central limit theorem the sampling distribution of the sample proportion, which I've written in here because apparently there's a way to upload pictures to Zoom, to the Zoom whiteboards, but I haven't been able to make it work. I can't find that option anywhere, so I'm just gonna draw it in there. So we can make confidence intervals for population proportion in pretty much the same manner that we do for means. We just use a different calculation for the sampling distribution, but all the logic is the same, right? And it's just instead of having X bar and mu, now I've got P hat and P. That's it. That's the only difference, right? Logically, it's the same stuff. So central limit theorem tells us this, that P hat, or the sampling distribution of P hat, is approximately normally distributed with a mean of P and a standard deviation of this guy, square root of P times 1 minus P over N. Now, we don't have access to P, which is literally why we're making a confidence interval, is we're estimating P, so we clearly don't have it. So what we can do is we can substitute P hat for P. Now, this doesn't have the same effect on the distribution as it does when we substitute X bar for mu, or when we substitute S for sigma. I know it feels like it should, but it doesn't. What we end up with is this. So the sampling distribution we're going to be using is this one here. So normal distribution with a mean of P hat and a standard deviation of the square root of P hat times 1 minus P hat over N. Let's see how that looks. All right, so here's our sample. We take a poll of Santa Barbara voters about whether they support the universal pre-K aspect of the Build Back Better plan, which is President Biden's human infrastructure bill. It's the one that news is going on and on and on about the cost of. I don't want to, $3.5 trillion is the cost that they're going on. I don't want to get into too much of that. I have my own political opinions on that, but it's a good way to ruin a video is start putting them in here. So of the 255 people we survey, 181 of them say they support the universal pre-K aspect of the bill. So what we want to do is make a 95% confidence interval for the proportion of all Santa Barbarans who support universal pre-K. Now, notice that our sample is Santa Barbarans, so our population is Santa Barbarans. We're not going to try and extend this to like the whole country, because that we didn't take a sample from the whole country. We would have extreme sampling bias. What we did was we took a sample from Santa Barbara, so we're going to generalize to Santa Barbara, and we're going to then explain what the result means. So let's go ahead and do that. So we had 181 out of 255. So we had our p hat is 181 out of 255. Let's go to the calculator, see what that number actually is. So 181 out of 255 is that 70 point. Let's call it that. Let's just call it 71%. That seems pretty close. About equal to 0.71. All right. So what we can say is the sampling distribution p hat, so capital P hat, is equal to n normal distribution with a mean of 0.71 and a standard deviation of this 0.71 times 0.29, which is 1 minus 0.71. I hope that's clear. Over our sample was 255. Right, so let's we'll jam that into the calculator and see what we get. Calculator, so we're going to get square root of 0.71 times 0.29 divided by 255, 0.0284. Okay. Okay. So we have a normal distribution now with a mean of 0.71 and a standard deviation of 0.0284. And we want to know, we're trying to make a 95% confidence interval. So we need to figure out how far to go on either side. So we need to know what the range is that we want to go. So the way we do that is with inverse norm, right? So my picture looks like this. Black picture looks like this. 0.71. And we need to know how far on either side we're going to go to capture 95% of the data. So I'm going to do inverse norm of 0.025 with a mean of 0.71 and a standard deviation of 0.0284. Let's go here. So I'm going to do norm.iv of, so X is the area, 0.25 with a mean of 0.71 and a standard deviation of 0.0284. Says that the left bound is going to be 0.654. And then the right bound, if I want to figure out what that is, we're going to have norm.iv of 0.975 now, with a mean of 0.71 and a standard deviation of 0.0284. And at that, 0.765. So my confidence interval is going to go from 0.654 up to 0.765 or 766. 654, 766. So this is 0.654, 0.766. So that's my 95% confidence interval. I'm 95% confident that the proportion of Santa Barbarans who favor the universal pre-K aspect of the Build Back Better plan is between 65.4% and 76.6%. It's a pretty wide range, right? That's like, it's 11% wide. It's fairly big. And we can do the same thing for 90% and 99. I think that's not what I asked for. I think I asked for like 60 and 80 here or something like that, right? 60%, 80%. So I'd say we're 95% confident that the proportion of Santa Barbans who support that aspect of the Build Back Better plan is between here and here, 65.4% and 76.6%. We can do the exact same thing for, let's say, 60 and 80. So if we have 60%, let me get an eraser here. Whoop, there we go. If we have 60%, that means that we're going to be here, right? This is going to be 0.6. So there's 40% outside, so there's 20% on either side. So I'm going to do inverse norm of 20%. Where am I at here? And 20%, and let's look at this again. 20% for this area here, and then 80%, because that's 0.2 plus 0.6 for this bound here. So let's go to spreadsheet. And so we can do norm.inv of 0.2 with a mean of 0.71 and a standard deviation of 0.0284 to get that value. And then the same thing for 80%. Inv of 0.8, the mean of 0.71 and a standard deviation of 0.0284. That. Right, so there's my confidence interval. I'm 60% confident that, I'm 60% confident that the mean is somewhere, or that the actual proportion is somewhere between 68.6 and 73.4%. Right, we can do the same thing for 80%. Notice this interval here is smaller than this one, but I have to be less confident, right? So we traded off some confidence in order to gain some precision. There's always a trade-off. Back to the whiteboard here. And then you can do the same thing for 80% as well. Right, for 80%, you have the middle 80%. We've got 10% on the left, 10% on the right, 80% in the middle. So the things you're going to do are inverse norm of 10% to get the left bound, inverse norm of 90% to get the right bound. And there you go. Now, there is an easier way to do this on your calculator. So let's go look at the calculator for a second. So I don't believe I have shown you this aspect of your calculator. I'm going to go to Stat and Tests. And there are some intervals in here, anything that ends in int. We're going to worry about the tests a little bit later, but those are hypothesis tests, which is topic 11. Topic 10 and onward, 10 is about hypothesis testing in general, and then 11 is about the first of our specific hypothesis tests. So if I wanted to make a one proportion Z interval, which is what this is, one prop Z int, go here and specify my confidence level and my X and my N. So let's just do the one we just did, right? We said 181 out of 255 people said that they preferred, they supported the build back or the universal pre-K aspect, 95% for a confidence level. Calculate, there we go. Notice that that was exactly what we got, right? 65.4%, 76.5%. This is actually slightly more precise. They're going one extra decimal place here. They're not using, I did 0.71, right? And they're actually using 0.70980939216, right? So more precise proportion. But they're getting the same thing that we got right over here, which was this, right? 0.654 to 0.766. 0.654 to 0.766, right? They rounded the 7655 to 76, or I rounded 7655 to 766. There's the same thing for T intervals. right? So let's go back and see what that looked like on our whiteboard here. This one, right? So when we were using this, we were making a 95% confidence interval. Let's just go ahead and do that. So, and then we'll see if it matches up. So this is going to be a t interval because we were using a t distribution. There is a z interval option in your calculator, and in my opinion, that option is stupid. We're never going to use it. The reason I think it is not worthwhile is that, let's go look at it. It requires that you know sigma. You might say, well, maybe sometimes we'll know sigma. Probably not. The reason probably not is that sigma, your standard deviation, is calculated using mu, your population mean, right? That's where you get the, like, mu is involved in the calculation of sigma. So if you know sigma, you're pretty much guaranteed to know mu, right? It's very unlikely that you'll be able to find sigma without knowing what mu is in the first place. And if you know mu, there's no reason to make an interval. You don't need to estimate it if you already know what it is. So the assumption that you know sigma is probably not a good, oh no, my calculator timed out. That's really awkward. Okay, I don't know if you can see the error message or not. I will say okay. That, I have to log in again, fantastic. All right, well, the thing I'm gonna do depends on using the calculator. So I'm gonna go ahead and pause the recording while I open the calculator up again. All right, it's been like just a minute or so. So let's go get the calculator back. So as I was saying, you want to, or there's a t interval function on your calculator as well. Let me reshare that up. So as I was saying, I don't think z interval is worthwhile. The chance that you know sigma but not mu seems exceedingly remote to me. And z intervals, you have to know sigma, right? When we don't know what the population standard deviation is, that's when we use a t distribution and therefore a t interval. So yeah, I don't think there's much point in z interval, to be honest. So we're not going to use them. So stat tests t interval. Now you have two options for your t interval. If you have the raw data, like if what I had given you for Jason's fish was a list of 11 fish weights, and you put that into your calculator, it will calculate the mean and standard deviation and sample size for you, and then make the interval. We don't have that. What I have is summary statistics. So I go over the stats. X bar was 8.56. S was the standard deviation. That was 1.12. N was not 255. It was just 11 fish. And then our confidence level we wanted was 95%. And 7.807, 9.312. If I remember right, that is pretty much what we found. I rounded off a little bit, right? So mine are very slightly different. So we had 7.808 to 9.312, right? So tiny little bit of rounding difference, but 7.808. Oh no, look at that. So exactly the same thing. So a little tiny bit of rounding difference, but nothing consequential. So the point I wanted to make here is I do not mind if you use the interval functions on your calculator. That's really what it's for. I will say that on a test, I may ask you to show me the calculation, right? So I may want to see, where'd it go? This calculation right here. But if I don't specifically demand that you do it on a test, you are more than welcome to simply use the interval function. I will always ask for an interpretation, like what does this mean, etc. So like there's not going to be a lot of, oh, just calculate this interval, great, you're done. You know the way I ask my questions, I always ask you to explain stuff. It's going to be like that on the test and on the homework too. So yeah, the calculator will do a really good job of helping you with the calculation, making sure you get it right. But it's up to you to interpret what that means. And that, by the way, is going to be a running theme going forward in this class, which is machines do the calculating for you and you do the interpreting. So to describe what the numbers that you get mean, that's kind of the way the world is headed, right? Where machines do all the calculating and humans figure out what those numbers are telling them. So yeah, that's really what I wanted to say about that. So I want to do a couple more examples. These are going to be like working backward kind of examples, or at least this one is. And then the next one is going to be, it's sort of a working backward thing as well. Yeah, so this is just to see if we can understand how to get confidence intervals by going the other direction. As I've mentioned before, I love Bloom's taxonomy. Really tells us, it lets us figure out, okay, how do we deconstruct things, right? I can use it to, saying this really badly, can use analysis, which is a higher level function, to help me understand the lower level functions, is the idea. That's what we're doing here. So let's say I make a confidence interval for proportion, and I get this for my confidence interval, 0.56 to 0.68. I want to know what is p hat and what's the margin of error. To understand what this is, you really have to be able to reconstruct. Did I leave myself a blank screen? I did. You really have to be able to reconstruct, or to understand how a confidence interval is constructed. So in general, confidence interval looks like this, right? Here is my point estimate, which is in this case, p hat. And then the left and right bounds, we said were 0.56 and 0.68. And so the question is, well, how do we find the p hat? Well, it's in the middle. So there's a variety of ways you can do that, but the easiest one is to average them. So if I take the average of these two numbers here, that's going to be in the middle of the two of them, which is p hat. So I would average them, 0.56 plus 0.68 divided by 2. Another way you can do it is you can say, well, 0.56 and 0.68 are 0.12 units apart, right? It's 0.12 from here to here. 0.12 is the distance. So if I break that up into two equal pieces, that's 0.06 in each half. So if I go 0.06 in from 0.56 or in from 0.68, they should lead to the same place, which is 0.62. Which is also what you get if you average them. So that means my p hat is 0.62. And the other question is, what's the margin of error? Well, the margin of error is the distance from the middle to one edge, which we just found is 0.06. That's it. That's the answers to these guys. Proportion of successes, we have said that p hat was 62%. Margin of error, we said that the margin of error was 6%. So this question was actually significantly easier than the previous ones. If you are given the confidence interval itself, it's very easy to reconstruct where it came from, so long as you remember how confidence intervals are constructed. That for p, what we're going to do is we're going to center our interval at p hat, and the margin of error is just the distance we go on either side. So if we get the interval, then the center of that interval is p hat, and how far it is from the center to one edge is margin of error. That's it. That's all you got to do. So a more practically useful for the researcher thing is sample size determination. So in general, as a researcher, the only thing you really have control over is how big your sample is. Everything else is sort of forced on, right? If you decide to take a sample of 50 people and you're surveying them about, let's see, what I think I have a setup here, right? So we're surveying, the proportion of Santa Barbarans who support lowering the Medicare eligibility age, which is another aspect of the BBB plan. Then all you can do is say, well, okay, if I'm going to survey 50 people, then you just go out and survey 50 people. But right, whatever they say is what the answers are, or it's what your data is. You don't have any control over what they say. You only have control over how many people you talk to. So the general thing to remember is that the bigger your sample is, the smaller your margin of error is going to be. And you can actually see that in the formula, by the way. I think that's over here on page 9. Right? There's an n in the denominator of the standard of the standard deviation. Right? So the bigger n is, the smaller that number gets to be. And this number is involved in figuring out the standard error, right? This is the standard deviation, excuse me. This is the standard error. And so this number is involved in calculating the margin of error. And so the smaller that number is, the smaller your margin of error is going to be. So in general, the bigger your sample, the smaller your margin of error. And that smaller margin of error is better, right? As we were talking about, smaller margin of error means less wide interval, which is a more precise interval. It narrows down where the population proportion is, which is the thing you're trying to estimate, more accurately, more precisely. So the question is, if you have a certain margin of error in mind, how big should the sample be to hit that particular margin of error? And we can figure that out by solving the margin of error formula for n. Right? So remember that the way we calculate margin of error in the first place is we do, let me get this black. So we do the margin of error is critical value times the size of the standard error. Well, the critical value, I'm going to call that T sub C. And the standard error is this, right? P hat times 1 minus P hat over n. So if you have a particular margin of error in mind, you can just plug that in for E and then solve for n. I'm going to do that here. You don't actually have to do all that. I will say this. Since you probably don't know what your P hat is going to be, or you don't have a guess as to what P hat is going to be before you do it, the most conservative one that you can choose is 0.5. I'm not going to go into the algebra too much. We could draw some graphs and show you why 0.5 is the most conservative one, but trust me that it is. And so if I just put in 0.5 here and here and solve for n, that's going to make this a little bit easier. Make the calculation a little bit easier. It's also the safest. It's going to give you the largest n that will for sure give you a margin of error that you want. Your margin of error will almost certainly be a little bit smaller than the one that you, a little bit smaller than you wanted, rather than you even asked for, if you take an n as large as this calculation gives you. So I'm just going to do a little bit of solving here. So we're going to say that E equals T sub C times all this stuff, square root of, I'm going to make these 0.5, so 0.5 for P hat. Then 1 minus P hat is also 0.5 over n. All right, so here's what I'm going to do. I'm going to divide both sides by T sub C. So we get E over T sub C is the square root of This is 0.25 in the top. 0.5 times 0.5 is 0.25 over n. I'm going to square both sides to get rid of the square root. So we're going to have e squared over t sub c squared is 0.25 over n. Now, 0.25 is a fourth. So this is 1/4 over n. And I don't know if you remember how to divide fractions, but that's basically what I've got. So I've got a fraction buried in another fraction, right? So the bottom is like n over 1. So this is 1/4 times 1 over n. What I'm doing is I'm flipping over the bottom and multiplying, which is how you multiply fractions, or how you divide fractions. So this whole thing is 1/4n. It's the right side there. So I'm just going to erase that and just say that that's 1/4n there. Just erasing it for room here. 1/4n. Now, here's a trick that you may or may not know, which is, so I'm sure you know from algebra that anything you do to one side of an equation, you have to do to the other one, right, to keep them balanced. Well, here's the thing. You can do anything you want as long as you do it to both sides. And the thing that I'm trying to solve for n here, and n is in the denominator. So what I'm going to do is I'm going to flip over both sides. And yes, that is actually a legal maneuver. So this is t sub c squared over e squared equals 4n over 1, which is just 4n. And then I'm just going to divide both sides by 4. So I end up with t sub c squared over 4e squared equals n. Now, there's a similar formula for this. For confidence interval, or for sample size determination, for means, right? This is for proportions. However, it's only really convenient if you're doing a z interval, if you're doing an interval using a normal distribution rather than a t distribution, because with a t distribution, the critical value changes. Oh, these aren't t sub c's, these are z c's. Gosh darn it, I gotta go change everything now. I'm so sorry. With a t critical value, the t critical value changes depending on the degrees of freedom, and the degrees of freedom depends on the sample size. So it's this big circle that you have to work your way through. I apologize. These aren't t's. I'm gonna fix these. These are all z's. T critical values are for t distributions. Z critical values are for normal distributions. So this is z sub c. So my bad there. There we go. So they're z critical values. Because we're using the central limit theorem here. We're actually using a central limit theorem, which says that sampling distribution of sample proportion is normally distributed, not t distributed. Yeah, so you end up with this z critical value squared over 4 times margin of error squared is n. So let's see how to use that. And by the way, you don't have to go do this calculation every time. You can just remember the formula, or ideally probably just write down the formula. So I want to find out this thing that I said earlier, proportion of Santa Barbans who support lowering the Medicare eligibility age. And we want our margin of error to be no more than 3%. So how many people do we need to survey? Well, oh, shoot. Sorry, I should have said we're making a 95% confidence interval. I did not say that. That's my bad. Just heads up, by the way, if the confidence level is ever not specified, just assume it's 95% because that's by far the most common kind of confidence interval. So 95% confidence interval, margin of error no more than 3%. So I have to know we got a Z sub C for 95% is the Z critical value, how many standard deviation or how many standard errors we have to go on either side of the mean to capture 95% of the data. And I don't know if you remember this from a previous video, but here is, sorry, it's here. If I want inverse norm, norm.inv of for 95%. So I'm going to use a mean of 0 and a standard deviation of 1. Tells me that I needed 1.96 standard errors on either side. So this is my Z critical value. It's the number of standard errors I have to go on either side of the mean to capture the area that I want. So I want to go 1.96 standard errors on either side. So let's go do that. Z sub C is 1.96. The margin of error, E, is 0.03. That's all we needed, right? So we have N is, I want to make sure I'm getting this right. I always forget this formula. Z sub C squared over 4E squared. Okay. So Z sub C squared, so we're at 1.96 squared over 4 times 0.03 squared. So this is the number of people I should survey. So I'm going to jam that in my calculator. Calculator. 1.96 squared divided by, let's do this, 4 times 0.3 squared. Parentheses. Those parentheses, by the way, are necessary. It would not do this correctly. Otherwise, 1,067 people, actually a little bit more, right? So it's 1,067.1 people. So if we only survey 1,067 people, our margin of error will be slightly larger than we wanted. So we actually have to survey 1,068 people, right? Even though this 0.1 of a person wouldn't normally round up to 1,068. 1,067 people gets us a margin of error that's very slightly larger than 3%, right? Because we need to survey 1,067.1 people. Well, we can't survey the 0.1, so we have to just tack on another person to account for that. So we have to do 1,068 people. That equal to 1067.1. So we need to survey 1,068 people, which will give us a margin of error that is actually slightly smaller than we were wanting. But if we do one less, it would be slightly larger than we were wanting. So we got to do 1,068 to do slightly better than we wanted. Okay, that's sample size determination. There's so much more I can say about confidence intervals. I do want to say this. You have actually encountered many confidence intervals in your life, almost certainly, unless you are completely oblivious to the news. So for instance, every time you hear something like President Biden's approval rating is 51% with a margin of error of 2.5%, that's a confidence interval, right? They're saying that their confidence interval is 0.51 plus or minus 0.025, right? They usually just say the 51%, but by giving you a margin of error, it tells you that it's a confidence interval. So anytime you see something like that, anything with a margin of error on it, it's almost certainly a confidence interval. And most of those that you see are like public opinion polls, which are all categorical, like yes or no kind of things. Very, very few of them are numerical data, which was the first thing we covered, right? These are much more scientific type things, whereas, what people think is a much more pop culture kind of thing that you're going to end up seeing more of. So these are the confidence intervals that you've seen before. Maybe some of the other ones too, depending on, how often you interact with scientific literature. I think I'm going to go ahead and leave the discussion there. That I know that's a lot, but I'm going to go ahead and leave the discussion there and stop the video so this can end at some point. So I will see you guys in the next video.